In this lecture, we will start talking about operating systems. So the first lecture will be an introduction. The material that we are going to cover in this lecture are going to be based off of the text with the title Operating Systems Concepts. And it's the ninth edition. The authors are Silberschatz, Galvin, and Gagny. And this is going to be focusing on the chapter 1, mainly of the text. Now in this lecture, I want to give you guys a recommendation. I feel that there is a lot of information and terminology that is going to come your way. So a better approach than just watching a video is to actually read the text. So I would highly recommend that you read chapter 1 of the text, which is going to give you a lot more insight into the terminology that we are going to use in this lecture. Having said that, let's kick things off by taking a look at what an operating system is. So let's try to answer that question. So it's essentially a program. And as you can see over here, our operating system is sort of sitting at this level there. At the bottom you have the computer hardware, and above the operating system level you have several programs, and we are classifying them as system and application programs. These could include a compiler, assembler, text editor, a word processor, a web browser, a database system. So there are several application programs that you could put on that level, which sits above the operating system. But underneath you have the computer hardware. We can talk about what goes in this level of computer hardware. We have, of course, the brains of the computer, the CPU. We will of course have the memory. Those are the two most important aspects of a computer. And apart from that, we also have the I/O devices. So for example, the keyboard, the mouse, a printer, a monitor, a hard disk. So hard disk is going to be considered in the memory, but all of those constitute the computer hardware. And on top of the operating system, you have the applications, which are controlled by several users. So for example, if any user wants to get control of the hardware resources, whether it be to run a user process on the CPU, or it be to access certain parts of the memory, or to be able to interact with the I/O device like a keyboard or a mouse or a monitor, it would need to interact with the user would need to interact with the computer hardware. Well, if we did not have this operating system level, then it would be very difficult for a user to let the computer hardware know exactly what it wants to do at each and every step. Starting off the process, loading things into memory, and managing the I/O. So there are lots and lots of steps that are involved in managing the computer hardware. And if we leave that up to each user, then it would become extremely difficult for the users to manage the hardware to be able to run an application program, which is why we have this operating system which sits between the users and the hardware. So it's an intermediary between the users and the hardware, and it's sort of giving a basis or a platform for the application programs or the system programs to run. So that's an operating system. And you've definitely seen several operating systems. The common ones are Windows, and you have Linux, and you have Mac OS, and you have definitely for phones, you have iOS, you have Android. I could list several more, but those are your typical operating systems. And as you might be aware, I've seen this happen a lot. Different operating systems being run on different computer hardware. For example, this is very common where on a Apple MacBook, which is essentially the hardware, you have a Windows operating system running on that. So you could have a variety of operating system on a variety of computer hardware. And of course, the operating systems themselves can be classified into several types. So we have real-time operating systems, we have batch operating systems, we have networked and distributed operating systems. So each one having a particular application, suitable for a particular application. So some need to be very good at scheduling and using the CPU resources. Some need to be very small. For example, the real-time operating systems or embedded operating systems need to be very small. So they come in a variety of types. And I hope that I've established one thing here, that the operating system is actually making the life of all the users very easy, because it's allowing them to be able to use the hardware without actually having to step through each and every step themselves. Instead, they are going to hand that off to an operating system that is going to take care of that starting of certain processes in the background. So it is going to be seamless as far as the user is concerned. So what are the goals of an operating system? Well, the first thing that is a goal is to be able to execute or schedule user programs. We talked about what a typical user program set could be, a text editor or a web browser. So to be able to go through those user programs and make solving user problems easier. So to be able to use the operating systems to make things easier, make the computer convenient. So as opposed to managing the hardware, the user managing the hardware, the operating system is going to manage the resources, the hardware resources, to be able to protect the computer and the and the users. So some users might not have very good intentions, and they might actually, be okay with overwriting on the operating systems, or doing things that should not be allowed. So in that case, you need some sort of protection that the hardware or the memory gets, and the operating system is going to protect the computer from the users. And actually, the operating system protects other users from the bad users also. And in all of this, the goal is to be able to use the hardware resources of CPU, memory, and several I/O devices efficiently. So those are our goals, and we can look at the operating system as a resource allocator, and we can also look at it in terms of a control program. So if you look at the resource allocator, the operating system has several resources. The CPU, the memory, and the I/O devices. So it is responsible to manage all those resources. So for example, which user gets control of the CPU at what time, which user process is able to interact with the I/O device at what time. So it manages all those resources and decides between conflicting requests for efficient and fair resource use. So some requests might be high priority coming from a certain user. Definitely those requests could be classified further into some generated by the user and some generated by the system. So system calls versus the user processes. So the operating system decides how the conflict can be resolved for efficient and fair resource use. And the operating system is also a control program, because it's going to control the execution of those programs while preventing errors and to prevent improper use of the computer. Like I mentioned earlier, some users might want to write certain parts of the operating system, or want to change certain parts of the operating system. Note that that operating system sits in the memory. If the users were granted all rights, all privileges, then some users might have the ability to change the operating system itself. So we don't want that, which is why the operating system needs to be in charge, be the control program that prevents that improper use from happening. Now the core of an operating system, the one program that runs all the time on the computer, is called a kernel. And everything else can be classified either as a system program, which essentially ships with the operating system, or an application program. A system program is one which is sort of asking the operating system to do certain jobs on its behalf. An application program is essentially a user benefit. So user is running an application um, uh, and asking for the resources. So apart from the application program and the system program, you have the kernel, which is the program that runs all the time, the core of the operating system. Now, what are the several different components of an operating system? Note that this is a program, so it needs to manage a lot of things. So we are going to have the operating system is responsible for process management, main memory management, data storage, protection system, networking, and user interface. So it allows for all these to go on seamlessly for a user in the background. So let's go through each and every one component, and let's briefly talk about them. So the first thing that we have over here is a process management. What is a process? Well, a program is a passive entity, but when a program is getting executed, then it's an active entity, which is called a process. So the activities of the operating system involved in process management could be from creating a process, deleting a process, suspending or resuming a process in case we have a page fault, for example. We talked about that in the lectures on memory, where we need to suspend certain processes and resume when we have a place for them in the memory. So we need a provision to, and we also need a mechanism to synchronize a certain process with a different process. So we need IPC, which stands for inter-process communication, to happen between processes, and that mechanism is also supported by the operating system. So creation, deletion, suspension, resumption, and a mechanism to synchronize processes. All of that is the responsibility of an operating system, and we can classify that as process management. Next one is your main memory management. So the operating system is responsible to keep track of which parts of memory are currently being used and by which user process. So all of those decisions are the responsibility of the operating system. Decide which processes to load when memory space becomes available. So are they going to be relative to the size of the process? Are they going to be related to the priority of the process? Are they related to the user process versus a system process? So all of those decisions are being made by the operating system. And those, when decided, they get loaded into the main memory, leading to the execution of those processes. The operating system is also responsible to allocate and deallocate memory space as needed to the various processes. Next, the operating system also manages the data storage. So this is the mass storage, the big data storage. And you can further classify data storage into a few items. So the first one being file system management. So the operating system takes care of the deletion and creation of several directories so as to organize information for a user, to give a very clean look to a user. And within those directories or even subdirectories, you will eventually have some files. And all of that is managed by the operating system, and we can classify that as the file system management, to be able to support primitives for manipulating these files and directives, and to be able to ensure that the storage is consistent and durable. Now all those belong to the category of managing the file system. And there are other types of management also. For example, the secondary storage or the mass storage management, in which the operating system manages all the free space does it have, and which processes or data or instruction is stored where, right? So to allocate storage, and also to do disk scheduling. So usually you will have one hard drive and one disk controller. So which process gets the to use the disk controller at what time? All of those things are being managed by the operating system, and we can classify that as mass storage management. Next, we could also have the I/O subsystem management. So in this, the operating system interacts with various I/O devices, input-output devices, such as keyboard, printers, mouse, monitor, uh, and it's managing all those devices, and we classify that as I/O subsystem management. And several aspects of that are being discussed here. For example, buffering, caching, and spooling. Buffering is how do you move data from the processor or main memory to the local buffer of um, the device controller that belongs to the I/O device. So there is a buffer that is part of the device controller or the I/O controller for every I/O device, which is responsible for buffering some local data. So that's buffering. That is taken care of by the operating system. Caching is to store the data, to be able to quickly access it. We have seen the concept of caching before. Spooling is typically used for example, for printers, where there is one printer and several printing requests are coming in, and they are put on a spool or a queue, so that the printer executes one print job after the other. And the I/O subsystem also has a general device driver interface. For example, a generic USB device driver that's managed by the operating system, and the users could also install drivers that are for specific devices that are not generic, but they are all managed by the operating system. Now, the responsibilities of this I/O system is to interface other system components. So all those other I/O devices, how do you interface that with your computer to manage those devices? For example, when does each I/O device get to interact with the computer, to transfer data between the I/O devices and the memory of your computer? And we also need to be able to detect when that transfer gets completed. So to be able to do that I/O completion, to detect I/O completion, which is essentially done by monitoring a hardware interrupt that comes from the I/O device. The next aspect of operating system or component of operating system is the protection system. So this is protecting the computer from a user, or from a user, or protecting different users from other users. And the problem arises because every user is sharing the same resource. So all the hardware is being shared, the operating system is also being shared. So that's the problem, and we need a mechanism to be able to protect the computer or the good users. So what is protection? Well, a mechanism for controlling access by user programs or processes or users to system and users resources. So who gets to the resources? To be able to protect that, we need a mechanism that falls under the category of protection. And that this protection mechanism needs to be able to distinguish between authorized and unauthorized usage. We can perhaps safely say that all the kernel space or the system calls are going to be authorized, but the user calls could be authorized or could be unauthorized depending on the nature of that request. So to be able to distinguish that is going to be the responsibility of a protection mechanism. Specify the controls to be imposed. So who gets, so how do we know who is authorized and who is unauthorized, who is privileged and who is not privileged to make certain changes in the operating system? So to be able to control that, we need to impose those controls and provide a means of enforcement. So once the control has been decided, to be able to enforce that is also the responsibility of the operating system. Next, we could have networking and distributed systems as another component that falls under the category of operating system components. A distributed system is essentially a collection of loosely coupled processors. And if you have worked in a research lab, you most often come across several servers that have several processors, but you can access those processors as a distributed system or on a network. The benefit of that is we get computation speed up. So because we are able to access a lot of processors as opposed to working locally, maybe we have only a few processors that we have access to locally. But as a distributed system, we could get access to collection of processors, which increases speed up in our computations, which increases data availability, and it also increases enhanced reliability. So it increases the reliability. Over here, the processes would be connected through a communication network. So for example, a local area network. A distributed system provides user access to various system resources. So for example, you can use several different processors, you can use the memory that is on those servers. So those are all your shared resources. Okay, so that's networking and distributed systems, and let's talk about the user interface to the operating system. And whenever you interact with the operating system, this is probably the one way you know it. So this is sort of the face of the operating system. Let me talk about two first, because this is the more common one, which is the graphical user interface. So this is essentially how you interact with most MacBooks and desktops and Windows machines. So you might see a desktop, Windows and mouse. This was developed by Xerox mostly, and popularized by Apple Macintosh. So this is our graphical interface between the user and everything else that is behind the operating system. That's the user interface to the OS. Or we could also have a command line or command interpreter as our interface, where you just have a prompt and you're typing in all your commands to run certain processes in the background. So the command interpreter is essentially a program that reads and interprets control statements. For example, the Unix shell. So this is either a part of the kernel, or it could be a special program. So commands such as run, remove, move, copy. So all those commands that you probably are familiar with are executed or typed into a shell, and that particular interface is considered to be a command line or command interpreter, which is another type of user interface. Now, usually this is what happens. For a local operating system, for a local computer, most people go with a graphical user interface. But when you are accessing things on a network, for example, a distributed system, a command line interpreter is usually preferred. So because the graphical user interface brings in all the graphics that need to be loaded, but the command line is very light in terms of the graphics, which is what makes it faster, keeps it faster. Okay, we are going to stop here with this and then start talking about system operation in the next video.